On first glance, a distant pass through the solar system feels like a non-event. Space is vast, planets and comets rarely cross paths in dangerous ways, and the phrase flyby suggests something routine and safe. Yet nature has an unnerving habit of taking our simplifications and twisting them. The interstellar body known as 3 Atlas is the latest reminder, entering our planetary neighborhood on a hyperbolic path. It has refused to behave like an inert ball of ice and dust. High-resolution imaging campaigns aimed at the nucleus have uncovered a bizarre and escalating anomaly, clusters of metallic structures, taking shape around the main body. At first, mission teams dismissed these glimmers as noise-dead pixels in detectors, scattered dust illuminated at odd angles, or processing quirks that vanish when better data arrive. But in this case, the opposite happened. As instrumentation sharpened, the anomalies did not fade into error. They consolidated into unmistakable forms with sharp boundaries and geometric facets, the kind of features comets do not produce. Even more unsettling, the phenomenon is not static. The swarm around Atlas appears to be multiplying, and doing so on a schedule far more orderly than random fragmentation would allow. What began as a dozen compact objects, each no bigger than a compact car, has swelled into a collection dozens strong, with individual units now closer to the size of small houses. By the most recent observation windows, astronomers counted hundreds of reflective bodies, some stretching over 200 feet in length, scattering light-like shards of bright metal against the pale green haze of Atlas's coma. The escalation has not been gradual or sloppy. It has vaulted forward in distinct steps, almost as if an invisible metronome were ticking off the doubling of numbers and scale. Scientists have even begun using the term quadrupling as shorthand in control rooms to describe the rapid pace of multiplication. Composition adds another layer of strangeness. Ordinary comets reveal fingerprints of volatile ice's water vapor. Carbon dioxide, carbon monoxide mixed with silicate dust. They are the frozen archives of the early solar system, fragile and dirty snowballs that shed gas as sunlight warms their surfaces. Atlas, however, refuses to match that model. Its spectra are rich with metallic lines, iron, nickel, and trace elements rarely emphasized in comet science. One can stretch the standard comet framework to argue that a metal-rich crust is being eroded, releasing shiny fragments into space. But such an explanation collapses when confronted with the coherence of the structures forming. Random chips and irregular flakes are what one expects from an exotic crust. What we see instead are repeated geometries, scaling upward with remarkable regularity, patterns of growth that defy a picture of chaotic. OUTGASSING. It is this tension between what comets are supposed to do and what Atlas appears to be doing that has shifted the scientific conversation. The debate is no longer a matter of whether Atlas is unusual. It is a matter of what kind of processes, natural or otherwise, could explain metallic objects multiplying in lockstep with orbital motion, and as its path takes it closer to Mars. The consequences of that process demand more than curiosity. They demand preparation. Mars has become the focal point of concern, not because Atlas is destined to strike the red planet outright, but because proximity alone transforms risk into something tangible. Initial orbital solutions painted a reassuring picture. Atlas would sweep past at a comfortable distance, leaving Mars unscathed. But that projection assumed a solitary nucleus shedding harmless gas and dust. The emergence of a metallic swarm has reshaped those assumptions. Each new body in orbit around Atlas is a potential projectile in its own right. Momentum is not erased simply because fragments were born from a parent. If the growing objects decouple under the influence of solar heating, tidal stress, or jet-like emissions, they could follow divergent paths. A single large fragment might miss Mars by tens of thousands of kilometers, while a smaller one shifted by a barely measurable impulse could be nudged directly into the Martian atmosphere. Planetary defense is not only about preventing Earth impacts, it is about safeguarding nearby worlds where scientific assets and future missions are at stake. Even a modest impact on Mars would have consequences far beyond a scar in the regolith. The Martian atmosphere is famously thin, less than 1% the density of Earth's at sea level. That tenuousness makes it fragile. Inject a significant dose of metallic dust and fine debris, and the balance of radiative heating and cooling can shift for months or years. For robotic assets like Perseverance and Ingenuity, as well as orbiters relaying data back to Earth, such disruptions are not abstract. Dust storms already pose operational hazards, occluding sunlight, limiting visibility, and interfering with communication. The addition of high-velocity, metallic particulates could create localized hazes that stretch into global veils, altering drag on satellites and challenging air-braking maneuvers for any new arrivals. The more unsettling prospect is a cascade of impacts. Imagine not one but several bus-sized objects slamming into Mars within weeks of each other, each at tens of kilometers per second. Such collisions would excavate craters miles wide and loft clouds of pulverized fines into the thin air. The dust would not settle quickly. Instead, it would linger, drifting across hemispheres, dimming sunlight and complicating solar power generation for surface operations. Even the delicate reservoir of water vapor in the Martian atmosphere could be affected, as dust particles provide nucleation sites for condensation, altering circulation patterns in ways that remain poorly understood. For future human explorers, such changes could be mission-threatening, altering landing conditions and degrading environmental stability. The troubling part is not simply the scale of the threat, but its unpredictability. Forecasting the trajectory of a single tumbling fragment is difficult. Forecasting the evolution of hundreds, each influenced by uncertain microforces and potentially electromagnetic effects, borders on the impossible. Monte Carlo simulations balloon with uncertainty. The moment swarm behavior is introduced, the very multiplicity of fragments amplifies the unknown. What began as an intriguing astronomical puzzle has, in a short span, escalated into a planetary defense scenario that leaves no easy solutions. The extraordinary nature of Atlas's metallic swarm has pushed scientists to explore hypotheses that stretch the boundaries of traditional comet physics. Standard explanations, sublimation, gentle fragmentation, or surface erosion cannot account for the orderly multiplication of dense reflective forms. Sublimation may liberate gas and dust, but it lacks the precision needed to arrange iron and nickel into repeated geometries. Fragmentation produces rubble, not coordinated growth. The behavior observed suggests some form of aggregation, assembly, or active organization, as if the environment around Atlas operates more like a forge than a freezer. One leading line of thought invokes electromagnetic phenomena. Space is far from empty. It is threaded with charged particles, plasma, and micron-sized conductive dust. If Atlas generates strong and dynamic magnetic fields, perhaps through internal currents or exotic mineral properties, those fields could shepherd metallic grains along organized paths. Conductive dust might coalesce along magnetic lines, colliding and adhering to form plates, filaments, or even more complex shapes. In this scenario, the apparent multiplication of objects is not spontaneous but field-driven, powered by processes that convert ambient energy into structural assembly. Yet even this hypothesis confronts a fundamental question. What energy source could sustain such precise and high-speed assembly in a body traditionally cataloged as a comet? Solar irradiation alone is insufficient to explain the rapid production of large metallic fragments, which implies either hidden internal power or an exotic mechanism previously unaccounted for in small body. PHYSICS, a more radical proposal imagines Atlas as a seed of interstellar origin, a programmable or chemically responsive substrate lying dormant in deep space, until activated by the sun's energy. In this model, the metallic anomalies are not separate fragments but emergent appendages, developing in stages according to an internal blueprint. Growth, replication, and even potential self-repair could be underway on a scale unprecedented for natural bodies. It is a daring leap, defying conventional assumptions, but the exponential increase of geometrically coherent structures leaves few alternatives if one is committed to remaining grounded in observable data. Another interpretation shifts focus from origin to operational signature. Exponential growth and persistent geometry are hallmarks of designed processes. If Atlas conceals a technological core, a probe shrouded in ice and releasing metallic units into space, then the swarm could represent miniaturized devices, sensor platforms, impactors, or shielding elements. The green coma and metallic spectral lines could be byproducts of these processes, rather than primary features. Within this frame, quadrupling becomes not a biological or chemical coincidence, but a deliberate production schedule. The structure's repeated geometries reflect intentional design, and their proliferation is a metric of throughput. Every hypothesis, whether natural or engineered, demands an energy. Accounting mechanisms to assemble and sustain order require more than sunlight alone, hinting at internal or exotic energy sources yet to be understood. The implication of all these hypotheses is profound. Atlas is more than an ordinary interstellar visitor. It challenges our comprehension of small body physics, the limits of natural self-organization, and even our readiness to anticipate unexpected behaviors in space. By forcing scientists to consider aggregation fields, like morphogenesis or engineered production, Atlas is redefining what we consider plausible in our solar system. Observational teams must now balance curiosity with operational planning, preparing for consequences that extend beyond Earth to neighboring worlds like Mars, where robotic and future human missions may intersect with the evolving swarm. As the scientific community grapples with Atlas's enigmatic behavior, operational planning has shifted from theory to tangible preparation. The Deep Space Network's massive 70-meter dishes are now dedicated to long-duration observations, gathering faint echoes and refining the swarm's kinematics with unprecedented precision. Supercomputers crunch vast Monte Carlo simulations, attempting to model hundreds of metallic fragments, each with unique size, momentum, and potential interactions with the parent body. Even slight electromagnetic effects or microjets could alter trajectories in ways that multiply uncertainty. Predicting the path of a single tumbling rock is challenging. Predicting the evolution of a proliferating cloud of reflective structures is an entirely new frontier. Direct intervention, once considered a possibility, is no longer viable. Intercepting Atlas itself is geometrically impractical and temporally constrained. Instead, planners are evaluating rapid response missions aimed at the largest or most threatening fragments, small chasers designed to nudge trajectories just enough to reduce cumulative risk. Yet this introduces further complications. If fragments are self-healing or actively replicating, disrupting them might exacerbate the problem rather than mitigate it. For the first time, planetary defense is confronting a multi-target, potentially dynamic threat that blends natural and possibly engineered behaviors. Each mitigation attempt must be weighed against the possibility of multiplying rather than minimizing danger. Mars, often thought of as a distant laboratory, is now a stage for operational vigilance. The atmosphere, though tenuous, is highly sensitive to injected dust and debris. A single metallic impactor, arriving at interplanetary velocities, could excavate a crater miles across, sending clouds of fine particles aloft. Multiple impacts in succession would create hazes that linger, altering the local radiative balance and complicating solar power generation. For surface instruments, Aero capture strategies for future Mars missions would require rapid revision, and even the fragile reservoir of water vapor in the atmosphere could be perturbed, potentially accelerating loss to space. For surface assets like rovers, sample caches, and instruments, these are not abstract hazards. They are vulnerabilities that demand careful monitoring and adaptive planning. Amid the operational urgency, a counterpoint remains central to scientific rigor. Extraordinary claims require extraordinary evidence. Sun geometric reflections could be illusions, facets reinforced by phase angle, or artifacts arising from observational cadence. Apparent multiplication may in part result from sampling intervals, rather than genuine exponential growth. Only when multiple lines of evidence converge spectra, polarimetry, time-resolved photometry, radar, and, if possible, resolved imaging from Martian orbiters can certainty increase. The scientific community has risen to the challenge, sharing raw data before processing, cross-calibrating analytical pipelines, and stress-testing models under immense time pressure. This collaborative, open approach ensures that discoveries are not skewed by individual interpretations and that the rapidly evolving scenario remains grounded in verifiable observation. While caution is paramount, so too is adaptability. Atlas's behavior is reshaping protocols for planetary defense and small body observation, pushing detection thresholds outward and emphasizing early identification. For future interstellar visitors, it is teaching a valuable lesson that readiness cannot be confined to Earth alone, and that our conceptual frameworks must accommodate phenomena that lie outside traditional expectations. As the swarm proliferates and Mars looms nearby, preparedness, vigilance, and open scientific inquiry have become inseparable allies. Ultimately, Atlas is telling a story that transcends the immediate thrill of observation or the practicalities of planetary defense. It is a tale about the universe's capacity for surprise, resilience, and subtle engineering, whether natural, engineered, or something in between. Traversing interstellar distances from star systems many light-years away, Atlas arrives with an intricate swarm that multiplies in some light, challenging every assumption we hold about small-body physics. The sheer fact that such a system could develop, survive, and manifest complexity in our solar system underscores the remarkable processes at work in the cosmos, processes that are only beginning to reveal themselves. Perhaps what we witness is an electromagnetic forge, a phenomenon of field-driven assembly in which metallic dust is orchestrated into coherent, reflective forms by energy flows we have yet to fully comprehend. Perhaps it is a seed-like interstellar device, lying dormant for millennia and activated only as it approached the Sun, a natural or artificial program blooming under the right conditions. Or perhaps it is a corner case of comet physics, a natural body exhibiting plasma dust, interactions and mineral behaviors never reproduced in laboratories on Earth. Each possibility carries profound implications for our understanding of interstellar matter, small body evolution, and the boundaries between natural and engineered phenomena for Mars and future explorers. The lessons are concrete. The swarm may turn out to be a spectacular, harmless outburst of metallic fragments, a remarkable but non-threatening phenomenon, or it may represent a category of interstellar visitor that defies conventional taxonomy, carrying with it real operational hazards that challenge how we plan missions, design instruments, and predict environmental interactions. The stakes are not theoretical. Dust deposition, surface impacts, atmospheric perturbations, and interference with orbital operations could reshape mission outcomes and scientific return. Each object in the swarm carries momentum, and each trajectory, no matter how small, has the potential to alter both observation and operational conditions. Yet, amidst the complexity, there is a reminder of the best instincts of the scientific endeavor: collaboration, adaptability, and disciplined curiosity. Observatories around the world are combining efforts, cross-validating observations, and refining models in real time. Instruments on Earth, in orbit, and on Mars work in concert to extract every photon, every radar echo, every spectral signature from the data stream. The community's response demonstrates the balance between caution and wonder, between preparation and openness to the unknown. Every measurement, every refinement, every contingency plan becomes part of a framework that can respond to phenomena that stretch the imagination without abandoning scientific rigor. In the final analysis, Atlas is both a warning and an invitation. It reminds us that the universe operates on its own terms, unconstrained by human expectations or traditional classifications. It challenges us to track with precision, model with creativity, and prepare for outcomes that may lie outside precedent. The swarm is a teacher, and its lesson is clear. Keep instruments honest, models flexible, and minds open, even when an interstellar object passes at a great distance. The real story is often unfolding in its shadow, and the processes, growth, and subtle dynamics that quietly transform our understanding of the cosmos. Atlas may never strike, but it has already reshaped how we perceive and engage with the universe, proving that vigilance, imagination, and disciplined inquiry are our greatest tools when facing the unknown.